Okay, let's continue. And today's topic in our schedule is about the so-called advanced force spectroscopy. And the main topic of the so-called advanced force spectroscopy is we want to add a segment of hole inside our the force curves. That means once the probe touched the surface, it reached the defined force, and then we let the probe to stay on the surface for a while, and then to study the stiffness or modulus change. So the purpose for this kind of force curve, and it's the same as the traditional the Lally indentation or the traditional modulus measurement tools done. It is used to study the so-called viscoelasticity of the samples. And the viscoelasticity is developed in the beginning of the 20th century along with the polymer chemistries. And because for polymers, they found the property of the polymers, we should consider the parameter of time. So basically, the viscoelasticity gives an idea that the elasticity, the main parameter to describe elasticity is the modulus. And we use the letter E, and sometimes you can use stiffness. And we use S. They used to describe the elasticity of the samples. The larger modulus or larger stiffness means the sample is more hard. And then for polymer and for those kind of gels or cells, something blah, 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 like that, they found the modulus or stiffness is not a constant any, as always. It is a function of time. And then we need to measure, or we need to characterize how it is related to time. So in that time, those physicists and gave up several models to describe the viscoelasticity, this kind of viscoelasticity. When they say viscous, in Chinese, it's 粘度. It's used to describe the property of the liquid or the fluid. When you swim in water, or you swim, I'm sorry, well, nobody swim in alcohol, but you all touch the alcohols, you can feel the viscosity of alcohol and the water is not the same. And the way to describe the viscosity, we use the traditional word, classic Newton's law. The hydrodynamic force we sensed by the fluid, it is proportional to the speed. And the speed, I just write down speed, okay? It is proportional to the speed. And the coefficient, we would call it eta. That's the viscosity, and this is the Newton's fluid law. And for the elasticity, we're starting with the Hooke's law. The force we sensed, it is proportional to the deformation. And the coefficient, we call it stiffness, or in Hooke's word, he's calling it spring constant. So for the true materials we are facing in our daily lives, we found many materials, especially those polymers, they are not pure elastic. They show some viscous, or it shows some fluid-like properties. So we combine them together. We call it viscoelasticity. And since you can say there is a speed here, so the viscoelasticity relationship, we need to say time term in the viscoelasticity. So basically, to describe that, they also starting from Newton's law. So the force will sense should be a combined. Our materials looks like a solid, so it shows the elasticity. And sometimes it will show viscosity, so I need to add the hydrodynamic force. And so let's give it a briefly define, okay? So we're starting from this Newton's law. We're starting from this, okay? Just put it here. So we think we are just compress a certain sample. And we compress this sample, it gives us we can sense a force. And we assume we apply the force in this direction. And we call this direction the Z direction. Let me see if I'm using the same word. If I'm using this, okay, I can use the Z. We apply force on the Z directions. So my equation can be written down as the when the deformation is 0, we call the Z is 0. That's why how we define the 0 point. So the force can be written down as this, and minus eta dz over dt. That's the starting point of our description. Okay, so we do the same thing. We define we define our shape. The area is A, and we define the length is Z0. Okay, or the length doesn't matter. Then we change these equations into the stress-strain relationship. And this will be, this one should be eta times Z0. Okay, right? That's the how we change the Hooke's law into the stress and the strain. No, I'm sorry. We think that they should be divided by A. Should divided by A. We divided by A on both sides. Oh yeah. Is the d epsilon over dt, and on the other, yes, eta z0 divided by A. Yeah, something like that. Okay, so and then we make some change. We call the so-called eta z0 A. We call it eta. We call it eta sigma. Okay, we just to want. I'm sorry, maybe not to use eta sigma. We use the eta. Let's just use say eta s. Okay, eta s. We just want to make this equation to be more simple, to show the stress strain stuff and to get rid of the length and the area. So our final equation will be written down as right, similar as we used on this slide. So the next question is our next problem is we try to make this one in a similar shape of the sigma equals to a E times epsilon. So we try to get it back to be something like the Hooke's law. To be something like the Hooke's law. Oh, I'm sorry. To be something like the Hooke's law. And then we will use a certain effective modulus to describe these materials. And then this kind of effective modulus should be a function of time. That's our task, or that's the task those great scientists they are facing. They try to make up something like this. Okay, so let's say how they do it. The first job is done by Maxwell, and his idea is if I have a material is viscoelasticity, it shows viscous and it shows it shows viscosity and it shows the elasticity. So I think in this way. So I think it is a serial connection of viscous part and the elastic part. And the viscous part, in their word, they use this kind of, they call this one damper. They call this one damper. And in Chinese word is 油壶. Sorry, 黏糊. Yeah, and then he used a spring to represent the elasticity. And Maxwell recognized this kind of viscoelasticity as a serial connection. And for serial connection, once we apply force on this model, we are combined the deformation, right? For serial, you apply force for two spring connect serial connection, you are combining the total deformation. So in Maxwell's model, the total strain should be the strain of viscous part plus the strain of the elastic part. And in the slide, it is using the D represent the damper of eta, and the S represent spring to represent the spring. Okay, so represent the elasticity. And so for a damper, he can introduce a eta, and for spring, he can introduce a modulus. And this eta, that's what I want to define in this on the board. This kind of eta s. Okay, and so the equation is easy. So the total eta. So the total eta is the eta of the damper plus the eta of the spring. Okay, and so he tried to get it back. So he tried to link it to the Hooke's law or to the Newton's law. So for the eta damper, it is hard for him to measure because in the Newton's fluid law, there is no deformation, but it is speed. So he took derivative damper part plus the spring part. Okay, and as such, the damper part is the d epsilon d over dt, and the spring part. And then for this part is easy. We can get the Newton's law in. That's the force divided by eta. And then for this part, for the eta s, since we consider it is a pure a pure spring, so we can bring the Hooke's law. And then this modulus in this for the spring, it should not be a function of time. So I can get it out from the derivative. So that's his final equation established. Okay, that's the final description step, the final equation. So our job is just to try to solve this one. Okay, so to solve this one, Max Wim think about experiment to say how I can better to solve this kind of the equation out, or how to better to describe his model. He made up an experiment like this. He call it creep. So he think about he think about the experiment. If I at time 0, I apply a large force on my materials, and since it is considered both the elasticity and the viscosity, it should give me a deformation. The deformation, he call it eta 0. I'm sorry, epsilon 0. And then, since it shows a viscosity, we should be able to say the epsilon is changed along the time. And then that's his the idea for this kind of creep deformation. That means the material is like some worms, it's just moving slowly. So he called his experiment the creep. So he need to hold a force at a certain time, and he want to say how the deformation is changed during a hold force. So to serve this one, his total idea is I need to get this equation out. So I need to better get a way to describe the epsilon change or the deformation change. So then we can bring his conditions into his model. And for his model, he just need to get the epsilon out. He need to get the epsilon out. So we could write it down from t is from 0 to t0. The sigma is 0. There is no force. There's no force, and we can tell, since there is no force, so this term is 0. And the force is constant 0, so this term is also 0. So the d epsilon t over dt is 0. Means the deformation does not change. The deformation does not change, just gives us the deformation should be a certain constant. And I write it down, the certain constant as the C. And now I do not have enough condition to solve out the epsilon C, the original deformation, right? Because for this kind of solution, I need to know t at 0, what's the epsilon looks like. So that's for the derivative equation solution. So that's I leave it there. That's the so-called the original condition. I don't care about that. My purpose or my key idea is about this term, about this part. Now, for T0 to T1, that's my game. I need to get this equation out. And so from T0 to T1, my sigma is sigma 0. And I hold the force, so it's always sigma 0. So that's easy. So the d epsilon t over dt is just the sigma over epsilon, and in this condition it's sigma. I'm sorry, write it down. 0 eta. Yeah. And plus this part, this one should be, and I hold the force, so this one should be 0, and so the total one is just sigma 0 divided by eta. Do I miss something? Did I miss something? The epsilon t should be time 0 plus a constant, huh? Should not be some. Yeah, it's okay. Yeah. Yeah, something like this. Yeah, and then hey, the force is constantly at the sigma 0, and we put it in, and the d sigma over dt should be 0, and the final result is the sigma 0 divided by eta. And then we can solve out our epsilon is a function of time, and it plus a certain value, and this certain value we need to solve it out. So we can use the t over t0 as our condition. No, sorry. D epsilon over dt equals to the sigma divided by eta plus, yeah. So when the t equals to t0, so d epsilon over dt is equals to the sigma 0 at eta plus this one. So this one out is decided by at this times the sigma speed. So it's about this one. So if we ignore this kind of if we ignore the deformation change from 0 to t0, we just consider at this point the speed is kind of reduced to 0, so we can ignore this term. So the original one, no, I cannot get it out. I'm sorry. I have to leave it here because the epsilon C2 need to be measured by by other conditions. I'm sorry. It should be some left term here. So the totally epsilon t is something like this. From 0 to t0, it is a constant epsilon c1. And from t0 to t1, it is changed with time equals to sigma 0 divided by eta times t plus certain constant. And so they can write it down to get the so-called effective modulus. And this effective modulus, we apply the epsilon from T0 to T1. So we can write it down as the sigma 0 divided by sigma 0 eta T plus eta C2. Right. So that's the final results. That's his final results. Yeah. So in his description, the modulus should be reduced with time. That's the maximum. That's the Maxwell model's results. He described the movement of the creep. We hold the force. The deformation should change against the time, and as such, the modulus, the effective modulus, will reduce as time. That's the results. And so besides Maxwell, there's another guy named Kevin, and Kevin developed another models similar with the Maxwell. He want to describe in this way. He think the elasticity part and the viscous part, they do a parallel connection. And for parallel connection, he think the force is a combine of damper part and the spring part. And we use the same term, we use the sigma and epsilon to put it in. So it should be the total sigma is the sigma of damper plus the sigma of spring. The sigma of damper, we can just use the Newton's law. That's the eta s times d epsilon over dt. And for the spring part, and we just use we just use Hooke's law, modulus times epsilon. Okay, and then the idea is we need to do similar thing as the Maxwell model. So we can do maybe we can do another kind of experiment. And the experiment Calvin's Calvin designed is the so-called relaxation. And for his design, he wants to make a deformation on my sample at a certain time t0. And after t0, I will keep the shape of my sample. For example, you can just drag your paper or drag your pen, and then you want to hold the length or the deformation of your sample. And he want to observe how the force is used to keep this deformation. So that's his experiments. And we call it is a reduction of the force. And so it's just the similar. From T to T, from 0 to T0, the deformation in itself is 0. And it's keep 0. So my sigma is 0. I'm sorry. It should be also some constant. Should be also some constant. Play the same games. Okay. So when T is larger than T0, my deformation now is held at certain constant value. It is at E0. Okay, then for the E0, for the epsilon 0, then I put these numbers in. The sigma T equals to the, and the, I'm sorry, this is the eta s d epsilon 0 over dt plus E0. And then this term is 0 out. Hmm? No, something wrong. What's going on? Mm, this one is keep constant. 0 segment is right, and epsilon is a constant. Epsilon is a constant. Oh, I'm sorry. I'm sorry. I'm sorry. I'm sorry. Sorry. I messed up the condition. I'm sorry, I messed up the model and the experiment they are doing. So this is a parallel connection, and the parallel connection is done by Maxwell. I'm sorry. Let's finish this one, then we can go back to the theory. I'm sorry. Uh, for the Maxwell, and for this one, it is the yeah, yeah. I'm sorry. So let's go to the let's do the Maxwell first. And the Maxwell is a serial connection. Yes, damper. Okay, that's the spring, that's the damper. And the total deformation should be the deformation caused by the spring and caused by the deformation of the damper. And then what we need to do is, I'm sorry, I messed up here, is we do a relaxation. We do a relaxation, not the creep. Yeah, that That should be correct. And for the deformation, and t from t to t0, the total epsilon should be 0. That's correct. Yeah, that's the correct. The epsilon should be 0, and the total epsilon should be 0. And when I put it back in this equation, the left side is 0 plus sigma over eta plus this one is also 0. So my force should be constantly 0. That's correct. That's the right term. And then t larger than t0. My epsilon now is constantly equals to eta 0. And then I put this back in my equations. And on the left side is 0 equals to eta over theta plus d sigma over dt. Yeah. And to solve this kind of equation, my sigma should have a solution form like A times E alpha t. Right? Because on the left side there's no time. On the right side it's both sigma and the d sigma over dt. So the sigma is should be an exponential function. Yeah, it should be something like this. And then we need to, our game is to solve out what's the alpha looks like. So I put it back in. 0 equals to A over eta E alpha t, and plus the alpha will goes out A alpha divided by E, and it's E alpha t. Of course, A equals to 0 is our solution, but that means this material is purely fluid or purely water, but that's not our conditions. So A equals to 0 is our solution. We just take it. I'm sorry, I write it down here. And the second condition is A does not equal to 0. If A is not equals to 0, you can divide it by A on A E alpha t on both sides. Then we give out 0 equals to eta 1 plus our alpha equals to negative eta O E. Yeah, that's the term. And so finally we get the sigma equals to A E negative modulus divided by eta times t. And that's the formation of the sigma, and we observe something curved like this. Yeah, that's correct. Yeah. And then we need to solve out Yeah. Then we need to solve out we need to figure out A. And then we put the T0 in. We put the time equals to T0 in. We need the experiment to give us a condition. What's the sigma looks like. And the experiment will define the sigma if we measure it if it's at sigma 0. If it is at sigma 0. And then you put it in, the sigma equals to A E T0. And then, I'm sorry, sigma 0. Then the A equals to the sigma 0 E right? It's something like this. Then you can give it back in. So our final results should be sigma 0 E negative E minus eta T minus T0. correct? Right? That's the final solution. When t equals to t0, the sigma will equals to sigma 0. That's the final result. So this one is to describe this curve, is to define this curve. And so finally, we have sigma, we have epsilon, we can write down the effective modulus is sigma divided by epsilon. That is that's the sigma 0 divided by epsilon 0. And the terms, that's the modulus. That's the effective modulus for the total materials. And this modulus is described and told us the modulus will change over time, and it follows the exponential function, and it reduces the time. How fast it is reduced, how fast it is reducing is decided by the modulus part and the viscous part. And that's the results of our Maxwell the model, and it used to describe the force relaxation. Okay, yeah, this is correct. So I write it down here. E minus T0 and the effective. Okay. Now we can go to Kelvin model. The Kelvin model is the parallel model. So it's a spring combined with a damper. So we're actually adding force. And we use the term of the stress and strain. So it can be write down the total stress equals to the spring part. I use the modulus times E epsilon. And for the damper part, I use the Newton's fluid law. So it is eta s d epsilon over dt. And then for this model, Kelvin described the creep movement. He described the creep movement. And so for creep, the creep is to we hold our force for a while and to observe the deformation change. So it's follow the same game from t0 to t0. The force we applied is 0. So the force is applied at 0. So we put it back into this equation. The epsilon should be 0. Okay? Yeah, correct. And when t equals to larger than T0. Okay, I write it down. From T0 to T1, my force is hold at sigma 0. So the good, I think there's no battery, but it's okay. Let's charge it for a while. So from T0 to T1, the force is hold at sigma 0. So on my left hand side is the sigma 0, and it is E epsilon plus eta ES d epsilon over dt. Right? Then for this kind of equation, we need to figure out the solution of epsilon. For solution of the epsilon, it is a little bit different with this one because for the relaxation one on the left side is 0, but for this one we have a non-zero term on the left hand side. So we need in the calculus we need so-called some special term, or we have some special solutions. So my final solution should also be some exponential function. So it's B E beta T. They should have this one. But when the T equals 0, we need to consider this the sigma 0 term. So I decided to add a certain term C here to say if it can better serve this kind of my solution. So I put it back in. So that one should be the sigma. Write it down small. B beta T plus C. Okay, so write it down. So the sigma 0 equals to the E alpha T and plus EC and plus eta S. There should be a beta out. That's the B beta, and that's the E beta T. Okay, so I want this equation to be constantly true. I need I can have the conditions is the EC equals to the negative sigma 0. Right? That's the way to get it solved. So the C is just equals to negative. This one, and then I need to figure out the B. Oh, sorry, this is not alpha. This is beta. I need to figure out the B and the beta. Of course, B equals to 0. That's one solution, but we don't like it, so we take B not equals to 0. So I can divide it by B on both sides. That's the E beta T plus eta S beta E beta T equals to 0. So that's the similar. That's the similar as this one. So my beta equals to the negative E minus eta S. So it's something like this. So finally, we can solve every term. So we can write it down. My epsilon equals to the B, and the eta negative eta minus eta S T, and it should divide yeah. Minus. Oh no. This is positive. This is positive. That's fine. Plus. Yeah. That's our results. So once at the t0, this so our epsilon should be something like this. It means it has a original deformation. It has an original deformation, and after that, the epsilon will change against the time. That's something like that. And then we need to decide the b, and that's the same game. We put it back in when t equals to the t0, and when the t equals to the t0. No, it cannot be decided, because this one will always be the zero. Yeah. It's just end of the game. That's it. And then we can similarly write down the effective modulus. That's the sigma 0 over b e eta over eta st plus. That's it. Yeah. So it's also an exponential function, but it's a little bit different with this one. Yeah, that's the creep for the Kelvin model. That's creep for the Kelvin model. Okay, so sorry, I messed it up. I just think the wrong way about these two equations. So totally the final game is for the viscoelasticity. The game is to need to figure out what's the modulus looks like. We'll write it down to be a function of time. And in 19th century, the Kelvin and Maxwell, they gave a basic description of the viscoelasticity. The Maxwell gave the serial connection, and he is used to describe the relaxation. And the Kelvin, he used his parallel connection. He described the creep. And both of them, they gave a description of the modulus is a change against the time, and it looks like they are all reducing against time. So that's the end of their stories. But in the 20th century, people found that it is not always correct to just use Maxwell's serial or Kelvin's combined. So nowadays, they just play the games similar as the resistance. So they put a standard linear combination for those things. We can starting with Maxwell, and it is a serial combination of the spring and the damper, and then I can parallel connection of another spring. So nowadays, they prefer to use this kind of standard linear solid models to describe the viscoelasticities. And nowadays, people use to write down the solution for these kind of terms in such way. So basically, they will do a creep. Sorry, I used the blue pen. And the creep is to observe the to observe the absolute change, or they can do a relaxation. To observe a force change. This is absolute. This is the force. Either way, it can work, and then their final result is to get the modulus change against time. And in the pure Maxwell, it should be something like this, and in the pure the Kelvin, it should be the function I just erased. But nowadays, people would just use the theta results to help them to decide what it should be looks like. That means I just use the exponential fitting on these curves. I would use the function like this. My E equals to a E0 plus several terms on this curve, several terms of exponential function on these terms, and each term is defined in Maxwell's way. In Maxwell's way, so that's the E1 times on the lifetime term is E1 over eta. So yeah, and then he can add several terms for this kind of fitting. And from the fitting results, it gives the what it looks like of this physical elasticity. So nowadays, the people do not establish their model first, but they just do experiment first, and from the experiment, they fit their results, and then go back establish their model. That's nowadays way for this kind of relaxation or the creep down, and they call this kind of model, or they call this kind of the fitting, the Maxwell model. So nowadays, if you search the reference about how people done the physical elasticity, they will prefer this kind of way. Just do creep or do relaxation, and then get the modulus against the time, and then do fitting, and then do fitting. In the afternoon, we will show you this process, and we will use some polymer samples to do a relaxation and do a creep, and we can say, okay, how this process is done. Okay, so let's take, I'm sorry, I messed up the mathematical deduction, and just took some time. And let's take 10 minutes break, and go back to say how AFM done this experiment. Okay, let's go to the so-called advanced force spectroscopy. This is used to do when we do force curves, and we try to conduct the classic creep and the relaxation on the AFM. And so the slide is about this three, and at the beginning of this slide, I list out something about I give a brief review of our the force curves, and about about the column probes, sphere probes, and the cone probes. And then we introduce a little bit of AFM nano indentation. The so-called AFM nano indentation is do the same thing as our ladder indenter did. The ladder indenter, it use a diamond probe to do force curve on the surface, and the AFM can also use the diamond probes to do the same thing. So for this same idea, the Bruker, the AFM also call it a ladder indentation, and it's actually the same as the force curve, but it is using a diamond probe to do it. And once, do we have diamond probe? No, yeah.
This one
That-
is really expensive.
Yeah, this one is really expensive, and it is not widely used. That one, not only due to the reason of money, it's just due to the principle. The AFM is a little bit different with that one. The AFM, we know the shape of our probe is something like this, and then once we press down, we apply a force to press down. And since we have a piezo or scanner about here, and so we really is moving the scanner down. We are moving our Z piezo, our scanner down. As such, we push the probe down. And since it is a cantilever connection, we apply force here. And on the left side, you know the beam, or you know the basic force. It will cause a shear force in this direction. And this shear force direction will push the probe in this way. And so finally, our probe is moving here. So the original one, let me draw it this way. Original probe is something like this, but after we apply force, it's something like that. So we will cause a lateral movement of the probe when we apply force. This kind of lateral movement is not what we want. But for small force, like we apply several micronewtons, this lateral movement is so tiny, we can ignore it. So that's why AFM is widely used for the polymers, for those kind of cells, gels, and for some not super hard the metals, like aluminum or blah blah, something like that. That's why we just need to apply small force. But if we want to study the materials like the Dr. Wei introduced yesterday, if we want to study the diamond, the modulation, or the mechanical property of diamond, or some super hard materials like the tungsten carbonate, for those things we need to apply large force. Maybe goes to several micronewton to millinewton, and in that condition, this lateral movement will be significant. So that's why this probe is not that popular, because people do not like this lateral movement. It changed the story. I want to apply on this point, but finally I push my sample away. So that's why the AFM, the diamond probe on the AFM is not that popular. Not just because of the price, but due to its application. But for the ladder indentation, it cannot apply quite tiny force. It cannot do the force as AFM did on polymer or the cells, but it can apply large force because their indenter is the perpendicular one. So their Z scanner is on top, so they can apply force perpendicularly. So that's the reason. So Bruker also have this kind of probe, but not very popular. So we also introduce how to use this probe. The game just to do some compensation of this movement. So Bruker need ask people to do some change when they do the force curves. So since it's not widely used, so I just jump this part and directly go to our topic today. That's the ramp and hold. Ramp and hold is the main component of the so-called advanced force spectroscopy. The idea is we want to apply a hold segment during the force curves, and for the advanced or for this ramp and hold function, and it is just used to do the viscosity. I'm sorry, to do the viscoelasticity. They want to repeat relaxation and the creep for the on the force curves. So this kind of let me say. Oh yeah. Let's start with the relaxation. The relaxations similar as the Maxwell's described. We make the samples had deformation, and then we hold this deformation. Oh yeah. We hold the deformation. We hold the deformation and we observe the force or sigma change against the time. And so in the AFM, we do it in such a way. Let's draw the force curve. So the classic force curve is the y-axis is the vertical, and after we do all the calibrations, now it's the force. And the z and the x-axis, the original x-axis is the z, and then we do a force curve something like this. Okay, and if we separate into the force against the time and the z against the time, it's simple. The z against time is I'm pushing down and I'm dragging up. And for the force, it's I have baseline and I have an attraction force. I reach the maximum force, and then I dragging out. I have the adhesion force and out. That's the force curves, and the force z against time. And then let's think about the creep. I'm sorry, relaxation. I need to hold my deformation. So the AFM to decide, let's do this way. Once I reach the maximum force, I let the z to stay on this height for a while. And then I lift up. And during this segment, I'm doing something like the relaxation did. I hold the sample's deformation, and since my sample's modulus is change against time, so I would think the sample is getting softer and softer and softer. The force will be relaxed, the force will be reduced. So I expect to observe something like this. And then that will be my final force curves. And if we try to capture the force curve back, if we still want to draw something like this, we may observe our force curves to be, but after we retract, our force is already reduced. That will be the force curves we are supposed to observe, right? That's for the relaxations. And so our experiment setup is something like, no, this. Huh? The slide is messed up. Yeah, sorry, the slide is messed up. Something wrong about here, but I will explain. So basically, we would do similar things as we done on the Hunter session. For the force curves, we need to define the ramp size, the how long distance of the Z travels, and we need to define the trigger threshold, which is the maximum force. And in the ramp and hold, in the ramp and hold function, you can see in the MCPF, the icon, we have a parameter set called surface control. And inside the surface control, we can type in the hold times. How long I want to stay on this distance. And that's the hold times. And typically, it is from 0 to 1 second. But in the facility setup, I think we can go up to I think it goes to 64,000. I think I don't know. We can go to 64,000. It's about 2 hours. It's about 2 hours. So actually, that's quite a long time. And usually, people will just hold maybe several minutes. That's the maximum. And usually, mostly they would do less than 1 second, and maybe some biological guys, they can hold it up to maybe several minutes, but this instrument provides about 2 hours. Yeah, that's about the time. And the next parameter is the so-called hold samples. The hold samples is how many data points you want to capture during the hold. How many data points you want to capture in the hold. So as we know, our next job is we capture the force, we capture the deformation. We will calculate stiffness and modulus out. So usually we want these hold samples to be as large as you can. Usually we give it about 1,000 or something. Yeah. And the next thing, I'm sorry, the slide is wrong, and we need to figure out in the afternoon. It is we need to hold Z or Z sensor here. So that's about a K difference we need to show in the afternoon. So let's talk a little bit thing about the hardwares. So we are just using a scanner to drag the probe to moving up and down. The materials used in our scanner is piezo. And the full name should be piezo ceramic or piezo materials. And it has the piezo electricity, which means if I apply a voltage on the materials, this materials, the crystal structure will change under the applied electric field. So it will have a deformation. And of course, in its term, it should be strain. Strain is proportional to the electric field applied. If I write it down in the deformation way, the piezo deformation will be proportional to the voltage I applied. So actually, how I drive my scanner to move is actually I apply voltage on it, and as such I can change the movement of my piezo. But again, the piezo is doing a tiny movement, so it will show a similar behavior as we described in this morning. It's the piezo itself, it has creep. The piezo itself, it has creep. So let's take a look on this hold. So how we achieve this kind of movement is we apply a voltage. And we change the voltage linearly until I extend my piezo. And then I want to hold my movement. So I want to hold the length there. How I do it? I will hold the voltage. The voltage against the time will be up. So that's my idea about how I want to control this movement of my scanner. But as we said, on this step, there is a creep. So ideally, I want my Z to be something like this. But the real situation will be the scanner will keep going due to the creep. So we usually would observe the Z is continually moving down. So ideally, I want to move my piezo linearly to reach this height. And I want to hold this height for a while and then moving up. But really, I reach this height, I hold the voltage. But the piezo itself, it has a creep. It will continue moving down, and its real movement is something like this. So this kind of phenomena is not people want. They want the height to be controlled as I designed. I don't want the piezo to be creeping. As such, change my force. So there is another setup in our instrument. They have a position sensor. And the name of this position sensor in the dimension system, they call it height sensor. So this sensor itself can read the current, read the real-time position of my piezo. For example, if my experiment is something like this, that's the time. I want my piezo to change from 0 nanometer to 100 nanometers, and then I want it to be hold at 100 nanometers, and then it retract back to 0 nanometers. That's my design. And if I just use voltage to control it, I will face creeping. And so this time I use the help of the sensors. And once I reach 100 nanometers, I do not hold the voltage, but I would change my voltage to make sure the sensor, position sensor, always give me the 100 nanometers. For example, I apply voltage, I reach the 100 nanometers, and due to the creep, the piezo wants to go down. But at this time, I can apply force, I can apply voltage to drag it back. So how I know how I should to change this voltage? I just use the position sensor to monitor the position of my piezo. So such I can adjust my voltage to make sure the scanner is hold at this 100 nanometers. So the instrument, our AFM instrument provides two options for the users. For if you want to control voltage, they say the software here, the hold type here is we hold Z. If I really want to control the height, the hold type here is we hold the Z sensor. Yeah, so in the afternoon, in the hands-on session, you can try both. You can try both. Yeah. If you hold the Z, you will see the piezo creeping, and usually people will done this on glass or on silicon, and because for silicon there is no viscoelasticity. You suppose you hold the height, the force will change. The force will be a constant, but if we hold Z, you will see the force is increasing because the piezo is creeping down. Yeah, that's the how we do it. But of course, if you are just hold Z sensor, it will hold this way. Use the sensor to monitor the piezo voltage, and piezo voltage will change, but the Z sensor will be a constant. We highly recommend the Z sensor, not to hold Z. Okay, and that's for the relaxation. That's about the relaxation. And we have another choice. That's the creep. And for the creep, it's the creep is much easier. So that's our original force curves. So our force is something like this, and my Z against the time, something like this. And then for the creep, when I'm sorry, let me say, yeah, a creep is done by Maxwell. Yeah, for the creep, no, creep is, I'm sorry, yeah, creep is done by Maxwell. For the creep, they want to hold the force, and to say how the deformation or how the strain is changing. And so at this time, we would make sure the force is a constant, and we would hold it for some time, and then I retract. Since my sample has the viscoelasticity, its modulus will change. For example, if my sample will be softer, you want to still hold this force. You want the sample is still to have this force applied. I need to compress more. So usually the Z will going down. And then retract. And then it will retract. That's the creep. That's the creep. We hold the force. And on this condition, when we draw force curve back, we would observe force curves. Let me draw it next to it, okay? We would observe force curve to be, that's the approaching. And since my samples, the Z will change. So once you retract, you will be the force curve will be something like this. Because the Z changed. So that will be the creep force curve. That will be the relaxation force curves. Or you don't like this kind of force curves, you can watch the force and the Z against time. It's okay. The software can give you both. Yeah, that's about the creep. And the creep setup is the same. It's similar to the relaxation. We have the force curve part. We have the surface control part. And for the surface control part, we just type in time and the samples. How many points you want to capture? Yes.
Yes. I have a question. When we measure when we hold the Z sensor.
Yeah.
But because my sample, the stiffness is getting smaller, so actually the deformation of the tip, or we can see the strain, is actually changed. But in an ideal theory model, the strain is kept as the same. So
yes, quite good point. Yes, that's true. That's true. So we would say for the AFM, for the AFMs, we cannot hold the deformation. I mean, we cannot keep the deformation as we did in the macro scales experience, because in the macro scale experience, they just compress the samples, the whole samples, so they can control the deformation. But for the AFM, yes, as Dr. Ma said, yes, we can only hold the position of the probe. As such, the deformation itself is changing. That's a little bit different with the models. So for myself, I would say the AFM creep is authentic, but the AFM relaxation is kind of pseudo relaxation. We do not hold the deformation. So for me, I always recommend customers to do creep, not do relaxation. The relaxation will face challenging from reviewers. They would say, no, this is not relaxation. Yeah. But luckily, the creep and the relaxation nowadays, we all use the Maxwell model to fit it, so it's okay. Yeah. But AFM still, this community still provided the relaxation, and they call it relaxation, but no, we think this is not true relaxation. The creep is real, the relaxation is pseudo. Yeah, okay, let me finish the creep. And for the creep, the hold type we type in here, we choose the trigger force. That means reach this force, we hold this force. Yes, and then the Z will change, and we will monitor it under the height sensor. That's the ramp and hold. That's a ramp and hold. So we will definitely try ramp and hold the first test in the afternoon. We will use different samples to show the results. We have the PDMS and the polystyrene, they are typical polymers. And we have a graphene, the HOPG. That's a pure crystal, and it is elastic. And we will not see a significant creep. And we will just show you how it works. Okay, so that's about ramp and hold. So ramp and hold can be used combined with the Bruker's force volume. The force volume is actually similar to the PeakForce QNM. They do force curves on each data point. And nowadays, with the ramp and hold, we can do creep or relaxation on each data point. And then we can capture a more complex mapping. we can do complex mapping with this force volume functions. So the afternoon we will in our hands-on session we will do a pure force curves, and then we can apply we can apply hold on the force volume. That's about the hands-on session in the afternoon. So we need to talk about more about the data process. So maybe Bruker should do more here, but the true case is we leave the data processing to our users. So after we do this kind of creep or relaxations, we capture a force change against time, and we capture the z change against the time, and nowadays the softwares, they can do the hold analysis, so they can directly take out this section. So let's focus on creep. So for the creep, the force is a constant. So we just capture out the z against the time. So we should be able to capture something like this. So, but then for the creep, if we take a look at the true creep curves, we should observe something like deformation. It's not the z. So we need to do some mathematical, or we need to do some data processing here. So the first, it is z. It is not the deformation. So I need to do z minus deflection. And the deflection is already a constant value because the force is a constant value. So it's the holding force divided by spring constant, the Kc. This one will be the deformation. And the Bruker is defining moving down as the positive value. So it's something like this. So we need to apply a lective to be something like this. That's our final deformation against the time. So that's the deformation. And then we need to use our force to divide it by this deformation. The force is a constant value. So finally we get the stiffness. And after stiffness, it's still not end of the story. We need to apply Hertz model. Stiffness is proportional to 2AC times modulus. So this AC need to be figured out by us. If we are using Snyder models, the AC is the deformation times the tangent alpha. If we are using Hertz model, the AC is the radius. So finally we reach here, and then we can do Maxwell fitting to get out the E0, EI, and EI over eta. That's the final data processing steps. I'm sorry, the Bruker is lazy and they stop here and leave all the tasks to our users. Yeah. So maybe Dr. Shi and Gordon, you can show the customers, you can show the users about this process and let them do it. Yeah, maybe we will develop the algorithm in the software later. But nowadays, we'll stop here. We'll stop here. Yeah. And also the JPK is the same. They stop here. Yeah. That's about the crib. And if you want to do the relaxation, it's the same thing. But the relaxation, as Dr. Ma said, the deformation is changing. The force is also changing. When we divide them, it's two changing numbers. Yeah. So that's about the data processing, and they can give out this one. The final result is to find out the fitting equation of this ramp and hold or the creep experiment. Okay, so besides this one, Bruker provide a more complex option. This complex option, Bruker gave it a name called ramp scripting. The ramp scripting is actually a function Bruker copied from the JPK materials. I mean the JPK bio AFMs, and of course after the purchasing them is together. So the ramp scripting is just give the user to make a customer owned or custom designed force curves. So they just want to do something like this. So let's give a brief explanation. So for this kind of force curves, for ramp and hold, it's defined. Moving up, hold, moving down, moving up, and then moving up. And sometimes the people, the researchers samples, they have the quite complex structures. For example, they have several layers. They have the layer 1, layer 2, layer 3, and they want to study the viscoelasticity properties of different layers. So they can use the AFM to indent on the first layers and then they hold there to study the properties of this layer. And then he indent probe more into second layers and then hold there and to study the properties. And the third layer, fourth layer, keep going. This is almost an essential task for the cells. Yeah, for the cells. Because for cells, first it has a membrane, and then it has cytoskeleton. It has some bones. Okay, so, sorry, just forgive my words. It's something like the bones, and then inside it's a matrix, kind of like a liquid, and then you may also have a nucleus. That's the cells, and for the cells is almost true. And for the polymers, yes, we may also need this kind of different layer structures, so that people invent such complex force curves. So they study the properties at each layers. So we can do the force curve something like this. When moving down, we reach a certain force, and we hold our Z, or we do a relaxation here, and then we keep going down, hold, and then we up, hold, and lift. So you can define your own force curves and to do something like that. So and as such, the Bruker just provide you different options, and in the script I show here, we provide 6 options. The first option is I'm moving down until I reach a certain force. Moving down and reach a certain force. The logo looks something like this. And this is just the first step of our force curves. I'm moving down until I reach the maximum force. And the next one is I'm moving up until I reach a defined force. Yeah, this one. And the third one is I hold the force. This is used to creep. And the fourth one is I'm moving down directly. I define a length I want to moving down, regardless of the force. And the fifth one is the moving up, regardless of the force. And the sixth one is I hold the Z. And the hold Z, I can choose hold Z or hold Z sensor. Both is included here. And in the afternoon sessions, the MCPF's icon is more advanced. It has a 7th icon here. That's for the modulation. It's for tomorrow's topic, the not the DMA. Yeah, so it's even complex than this one. Yeah, but we can give it a try to say the final force curves. So the function is quite simple. It requires you to know your structure very well, because when you're moving down, you don't want to go to the 3rd or 5th layer or even damage your samples. So this kind of experiments requires you do some previous preliminary data, and then we can continue this one. Yeah. And let's show an example, and we can end the morning session and goes to the hands-on session. And Bruker did one experiment, and not by Bruker, I think it's by some professors in Paris or something. Sorry, in France. And he is doing just a demonstration, and he has an E. coli. He has an E. coli, some bacteria, and put it on the polystyrene substrates. The polystyrene is just I'm sorry, not polystyrene. It's on glass. It's on glass. It's on our glass vials. And then on this glass vials, he is doing this. He's doing. Let me think. He's doing what? Hold force. Yeah. Yes, he's doing the correct thing. He is doing the creep. He's doing the creep, and he did a force volume. On each point, he has a creep experiment, and he hold the force for 5 seconds. So he hold the force for 5 seconds, and then he can capture the Z change against time on different regions. He has the live E. coli, he has the live E. coli, he has the dead E. coli, he has the glass. And you can see on glass the Z almost not change. But for the dead E. coli, the dead E. coli is dead, but it's still some kind of soft. So it shows some creep experience. And for live E. coli, the live E. coli is live and is the most soft. So it shows this kind of a significantly creep. And And since Bruker did not give the solutions about the data processing, and our professors, our users don't want to do the job for Bruker, so they stop here. So they do not fit the curves as we showed on the modulus. They just fit the curves on the z. So they just fit the curve on the z, and they show something like this. Of course, this f, this k means nothing to them, but the exponential, the lifetime term means something, because this time term won't change due to our data processing. So he took out the life terms and take it out to say for the live cells, it decayed more slowly than the fixed cells. That's just the same as our life experiments. When you are alive, you are kind of soft. When you are dead, sorry, it's kind of hard to push. That's the true for, and same as our experience. And he did this, and I think they published the results, and Bruker used this as an example about the ramp and hold or ramp scripting to study the viscoelasticity. Okay, so that's about our topic today, to give a description of the viscoelasticity. And from today's setup, we can say we study the viscoelasticity just follow its definition. We just want to get the modulus or stiffness as a function of time. So we just measure them against the time to say how it changes. But if the people are doing some real the elastic samples, like people are doing something like the bones, like the tooth, like the cartridge, those things are mainly crystals. They are hard, so their decay of modulus and the stiffness will be quite soft. It usually takes several hours. They can observe the creep or relaxation. So in all this, the people want to develop another way to do it. So in the classic, they do on time, and then for the more advanced way, they do the frequency. They do the frequency, and so they call today's topic. We call this kind of technology time domain. Time domain measurement is the creep and the relaxation. And for the frequency domain, they call their technique dynamic mechanical analysis, DMA. And tomorrow's topic, we will use about a morning to discuss the DMA process. And DMA, we can do both on the non-indent or on icon. And of course, Dr. Shi has, they can use some temperature stuff. They can also do the DMA analysis. So our facility can provide different way to do this analysis. So tomorrow we will talk more about the DMA, and the DMA is just do different frequency stuff, and give another way to describe the viscoelasticity. Okay, so I think that's all today, and we will go back on the hands-on session this afternoon, and we still have some QNM not done, right?
Yeah.
Yeah, we may finish the QNMs and then go to the ramp and hold and ramp scripting. Okay, thank you so much.